Hello everyone, I am Evame Giranido, first year BSCE 1M C13 from USTP. And in this video, I am going to solve a physics problem, work, and energy. So let's get into it. And in this video, this is our problem example. A block of mass m equals 5.8 kilogram is pulled up at theta is equals to 25-degree incline as in figure 1, with the force of magnitude F is equals to 32 N. A. Find the acceleration of the block if the incline is frictionless. B. Find the acceleration of the block if the coefficient of kinetic friction between the block and incline is 0.10. Our first step in this problem, as it would be with most problems involving forces acting on an object, is to draw a free body diagram of the mass that's situated on the ramp. Since there is no friction in part A of the problem, we do not have a frictional force pointing to the left along the axis here. We simply have the pulling force that's pulling the object up the ramp, the normal force that's acting perpendicular to the surface of the ramp, and then the force of gravity, which of course acts straight down. Now in most problems in which a box or any other object is on a ramp, it's going to be helpful to take the Fg force and break it into its components. There's going to be a component along the surface of the ramp, and then the component that's acting perpendicular to the ramp. So let's go ahead and do that. And when we do that, it turns out that the component along the surface of the ramp is Fg sine theta. The component that's perpendicular to the ramp is Fg cosine theta, and that will always be the case. It might also be helpful to remind ourselves that Fg is same thing as mg, so we can actually replace each Fg with mg. The next step after drawing the free body diagram is to apply Newton's second law, which is the following. The sum of the forces is equal to the mass times the acceleration. Typically, we need to apply Newton's second law to the both x and y direction. So why don't we try in the x direction first? In fact, we're only going to need to apply this equation in the x direction. Because in the y direction, it should be pretty clear that the object is not accelerating at all. In other words, the box is not lifting off the surface of the ramp, and nor is it digging into the surface of the ramp. So, we do not need to apply Newton's second law in the y direction because the sum of the forces in that y direction is equal to 0. So, we will only focus our attention in the x direction. And from our free body diagram, we see that there are two forces acting in the x direction. We have the applied force F, and then we have mg sine theta. Don't forget that because mg sine theta is pointing leftward, that it's going to actually be a negative force. So let's feel those two, some of the forces. Again, note the negative sign, and now we can fill in the known values. And at this point, simplify the left side and then afterwards divide both sides by 5.8. And when doing so, the acceleration turns out to be 1.38 meters per second squared. So that's our answer for part A. Now let's turn to part B, which is essentially the same as part A, except the only difference is that there now is kinetic friction acting between the block and the surface of the incline. So that means we just have to add one extra force to our free body diagram because the block is being dragged up the ramp. The kinetic frictional force will point opposite to that directions down the ramp. We've labeled that force F sub k, which simply stands for kinetic frictional force. Once again, there is no acceleration in the y direction, so we can focus our attention exclusively on the x direction when we use Newton's second law. We once again have the positively directed applied force. It's positive because it's pointing up the ramp. And then these two forces, because they're pointing down the ramp, we can assign a negative sign to them. So we'll go ahead and plug those into the sum of the forces. It turns out that F sub k, the kinetic frictional force, can be written using the following equation. The coefficient of kinetic friction multiplied by the normal force, we want to note for the normal force that that's actually equal to mg cosine theta. Once again, remember there was no acceleration in the y direction, so that means that the normal force is equal in magnitude to mg cosine theta. They essentially cancel each other out, and that's why there is no acceleration in the y direction. So in other words, the normal force can be set equal to mg cosine theta, so we'll go ahead and do that. We are now ready to substitute in all the known values. Simplify the left side and then divide both sides by 5.8 given the acceleration, and you should get a result of 0.49 meters per second squared. Notice this acceleration is smaller than the one in part A, which certainly makes sense because there is friction acting between the block and the ramp, and that's kind of slowing down the acceleration of the object.